Welcome to the deep dive. Today we're tackling something that feels, well, most super futuristic and also kind of already here, artificial intelligence, AI.
It's definitely a hot topic.
Yeah. And if you immediately think, I don't know, thinking robots from movies, that's part of it, sure. But let's start simple.
Good idea.
Basically, AI is about making machines that can do tasks that, well, usually need a human brain. Things like learning stuff, figuring out problems, making choices.
Exactly. And today we're not just talking about the latest shiny AI gadget you saw online.
Oh,
We're actually going way back. We're going to trace the whole story from ancient ideas, believe it or not, right up to the complex systems we interact with now.
think of it like an archaeological dig for ideas. Finding the roots planted by thinkers, inventors, maybe even storytellers who dreamed up artificial minds ages ago.
That's a great way to put it.
So our mission for you today is pretty straightforward. Give you a clear, hopefully engaging rundown of AI's history. The big moments, the bursts of excitement, even the times things kind of slowed down.
The AI winters, as they're sometimes called.
Exactly. We've sifted through a lot of material to pull out some surprising facts and hopefully make it all make sense. Okay, let's dig in. Where does this story even begin?
Well, it's actually pretty amazing when you realize the idea of, like, making artificial beings goes back centuries, millennia even, to myths and legends.
Really? Like what?
Okay, so take the bronze giant Talos from Greek mythology. He was basically this automated guardian for Crete.
An ancient security robot.
Kind of an early concept, right? An artificial thing built for a job.
Wow, okay. What else?
Then there's Pygmalion, the sculptor. His statue famously came to life.
Oh, right.
Yeah.
That story speaks to that deep human urge, maybe, to create something like us, blurring the line.
Exactly. And it doesn't stop there. Even in the Middle Ages, you find these legends, like the homunculus, this tiny artificial person made through alchemy, supposedly.
Right, and the golem.
And the golem, brought to life with mystical words. What's fascinating is these old stories often bump up against the ethical questions, What does it mean to create life? What could go wrong?
Yeah, the responsibility aspect.
Totally. And if you jump forward to, say, Mary Shelley's Frankenstein, or that play, R.U.R.,
Oh, Rossum's Universal Robots. That's where the word robot comes from, isn't it?
that's the one. They're exploring the same fundamental stuff, but now thinking about, actual technology.
So it wasn't just stories and myths. People were physically trying to build things too, weren't they? These
Automata.
Oh, absolutely. Automata. Really intricate machines, often shaped like people or animals, trying to mimic life.
Like clockwork people.
Sort of, but sometimes incredibly sophisticated. You had figures like Al-Jazari way back in the 13th century or Jacques Vaucanson in the 18th century building amazingly realistic mechanical figures. His digesting duck was famous.
Yeah, digesting ducks, seriously.
And, get this, in ancient Egypt and Greece, some people actually believed certain statues had real minds inside them.
And legends popped up about automata with, like, magical powers. Roger Bacon was supposed to have this brazen head that could predict the future or answer questions.
Okay, that's stepping into fantasy, but it shows the fascination, right? This mix of incredible craftsmanship and this deep desire to make inanimate stuff seem intelligent.
It really does. But look, it wasn't all myths and mechanics. To get to modern AI, there was some serious philosophical heavy lifting involved, too. Logic, reasoning.
Right, the thinking behind a thinking machines.
Exactly. The 17th and 18th centuries were huge for this. You had Francis Bacon championing empirical evidence, learning from observation inductive logic.
So not just assuming things, but learning from data, essentially.
Pretty much. And then Thomas Hobbes famously said, reason is nothing but reckoning. Calculation. The idea that thinking itself could be, well, mechanical.
That's a big conceptual leap. Thinking it's calculation.
It really was. And you see it made physical with Blaise Pascal inventing the first proper digital calculator.
Okay, the Pascal.
Yep. And René Descartes, he saw animal bodies as complex machines, pushing that mechanical view of life further.
And Leibniz, he has some big ideas too, right?
Oh, Gottfried Wilhelm Leibniz, amazing foresight. He dreamed up this universal calculus of reasoning. Basically, a symbolic language that could, in theory, solve any logical argument mechanically.
Like a universal logic machine.
That was the aspiration, an automated system for thought. Incredible stuff for the time.
That sounds mind-blowing for back then.
It was. And around the same time, you get Daniel Bernoulli talking about utility, super important for how AI weighs options today. David Hume dug into induction, how we learn from patterns, which is core to machine learning.
Okay.
Thomas Bayes gave us his theorem on probability fundamental for AI dealing with uncertainty. And of course, George Boole invented Boolean algebra.
The language of computers.
Wow.
True, false, ones and e's.
The absolute bedrock. And even later, Samuel Butler, 19th century, speculated about machines actually becoming conscious.
It's like all these different people were adding pieces to a puzzle they couldn't even see fully formed yet. Okay, so we've got myths, automata, philosophy, logic. What's the next big shift? When does it start to look more like AI?
Right, so the 20th century is where things really start coalescing into an actual field. Several key things paved the way.
Okay.
You had Bertrand Russell and Alfred North Whitehead with their huge work, Principia Mathematica. They showed that a lot of math could be boiled down to formal logic, which suggests
That maybe math reasoning could be mechanized.
exactly. And then someone actually did it, sort of. Leonardo Torres Quevedo built a machine that could play chess endgames automatically.
Wow, a real working example.
Yeah. And around the same time, you get the Ising model in physics, which turns out to be an early version of a recurrent neural network, a system that can kind of remember things.
Okay, neural networks are starting to appear conceptually.
Yep. But there were also discoveries about limitations, Kurt Gödel's incompleteness theorems, and Alan Turing confirming the halting problem.
Turing. Big name here.
Huge. These basically showed there are fundamental limits to what algorithms can ever do. Some problems computers just can't solve definitively.
So excitement, but also understanding the boundaries.
Right. And inspired by the brain, Warren McCulloch and Walter Pitts created the first mathematical model of an artificial neuron, an artificial neural network.
That sounds critical for modern AI.
Foundational. Then the term cybernetics was coined studying control and communication in animals and machines. It created a bridge between disciplines.
Okay.
Game theory popped up, analyzing strategic decisions, super relevant for AI agents. And crucially, Alan Turing, again, wrote his report, Intelligent Machinery.
The first AI manifesto, you call it.
Pretty much. He laid out key ideas, even talked about neural network approaches, and Donald Hebb proposed his theory for how learning could happen in brains' neurons that fire together, wire together, basically.
It really feels like the strands are coming together now, which leads us to that famous conference.
The Dartmouth Conference, summer of 1956. This is widely seen as the official launch party for AI as a research field.
The birth certificate moment.
You could say that.
Huh?
Organized by folks like John McCarthy, Marvin Minsky, Claude Shannon. And it was McCarthy who actually came up with the name artificial intelligence for the event.
Wow. So that's where the name itself comes from. What happened next? Did things take off immediately?
Oh, yeah. There's a real burst of activity. Early programs started appearing. Programs that could play checkers pretty well.
Checkers, okay.
Early attempts at chess, too. And the logic theorist program, this was amazing, it could prove mathematical theorems from Principia Mathematica automatically.
Proving theorems. That sounds pretty intelligent.
It was impressive. John McCarthy also invented Lisp, the programming language that became like the main tool for AI research for decades.
Lisp, right.
Researchers built programs for geometry theorems, too. And the General Problem Solver, or GPS, a really ambitious project aiming for one program to solve lots of different kinds of problems.
Ambitious is right.
And the MIT AI Lab was founded, becoming this major center for AI work.
So a lot of focus on logic, problem solving.
Yeah.
What about those neural networks you mentioned? Were they part of this early wave?
They were there, but kind of in the background compared to the symbolic AI approach, the logic and rules stuff. But yes, people like Ray Solomonoff were laying mathematical foundations for a general theory of AI, including learning. You had early programs doing symbolic integration in math, mimicking how students solve calculus problems. The first industrial robot arm, Unimate, showed up on assembly lines.
Practical applications starting early.
Yep. Programs tackling analogy problems, showing some abstract reasoning. And interestingly, the first deep learning algorithm, multi-layered networks, was actually developed in the Soviet Union back in the mid-60s.
Really? Deep learning that early?
Yeah, though it didn't really catch on widely then. Lotfi introduced fuzzy logic, letting computers reason with maybe instead of just true-false.
That seems useful for the real world.
Very. The resolution method was a breakthrough for automated theorem proving. Joseph Weissenbaum created ELIZA.
The chatbot therapist.
That's the one, mimicking conversation. Then the Dendrel system showed AI could help with real science, figuring out chemical structures.
Impressive.
Stochastic gradient descent, a key math technique for training today's big models, saw early use. Maxima was a powerful system for symbolic math. Shaky, the robot at SRI, could navigate, perceive, and solve simple problems in the real world.
Shaky. I've heard of shaky.
A classic. Roger Schenck developed ways for AI to understand the meaning behind language, and the first big international AI conference, IJC AI, kicked off.
That is a ton of activity in, what, 15 years or so?
Yeah.
Sounds like they thought they were on the verge of cracking it.
There was huge optimism, definitely, but then came the chill.
The first AI winter. Right. What happened? Why did the momentum stall?
Well, fundamentally, the early optimism led to some pretty wild predictions and promises that the technology just couldn't deliver on yet.
Overhyped.
Yeah, a bit. Scaling these early techniques up to complex, messy, real-world problems proved much, much harder than expected. The computers weren't powerful enough, the algorithms had limits.
So, reality check time.
Big time. And this gap between the hype and the reality led to disillusionment. Funding dried up significantly. This is the first AI winter, kicking off around the mid-1970s.
Was there a specific trigger?
A key moment, especially in the UK, was the Lighthill Report. It was pretty critical of AI progress and led to major funding cuts there. But it wasn't just practical limits. Philosophical critiques started getting louder, too.
Ah, the can machines really think. Debate heating up again.
Exactly. John Lucas used Gödel's incompleteness theorems to argue computers could never fully replicate human minds. Hubert Dreyfus wrote a scathing critique of AI's core assumptions, arguing human intelligence isn't just symbol manipulation.
Like there's more to it than just rules and logic.
That was his point. And then John Searle came up with his famous Chinese room thought experiment.
Oh yeah, the Chinese room. That argues even if a machine acts like it understands Chinese, it doesn't really understand.
Right. Precisely. It questioned whether symbol manipulation equals genuine understanding or consciousness. So you had practical hurdles and these deep philosophical challenges hitting at the same time.
Sounds like a tough time for AI researchers. Did everything just stop?
Not completely. Things definitely slowed down, less money, less hype, but important work continue, quietly laying foundations.
Like what?
The Prolog programming language was developed important for logic programming. New planning systems like abstrips and NOAA tackled how AI could create step-by-step plans.
Planning seems pretty crucial for intelligence.
It is. And MYCN, an expert system for diagnosing blood infections, showed that even with rule-based systems, you could achieve expert-level performance in narrow domains.
So specialized AI could still be useful.
Right. Marvin Minsky developed his idea of frames, ways to represent common sense knowledge. The Metadendral program actually made novel scientific discoveries in chemistry by learning rules from data.
AI making discoveries, that's cool.
Yeah. There was progress in understanding dialogue structure. The Stanford cart was an early self-driving vehicle effort, and researchers worked on non-monotonic logic, how AI can reason when facts change or are uncertain.
So the seeds for future growth were still being planted, even in the winter. What brought the spring? What sparked the next wave?
Things started warming up again in the 1980s. This is often called the second AI summer. Two big things drove it. One was the return of neural networks under the banner of connectionism.
Neural nets again. I thought they'd faded.
They had, but key breakthroughs brought them back. John Hopfield showed how certain networks, Hopfield nets, could learn and stabilize, but the really big one was backpropagation.
Backpropagation. Sounds important.
Hugely. Jeffrey Hinton, David Rumelhart, and others popularized it. It was finally a workable way to train networks with multiple layers, letting them learn more complex things. The book Parallel Distributed Processing was massively influential.
So better ways to train these brain-inspired networks.
Exactly. And it sparked a big debate. Symbolic AI versus connectionism. Logic versus learning from data.
And the second driver of the 80s boom.
Expert systems. These rule-based systems, like MYCIM, but for lots of areas, actually became commercially successful.
Ah, AI hitting the marketplace.
Yeah, companies use them for financial analysis, diagnostics, configuration. It showed AI could deliver real business value, at least in specific niches.
So renewed research interest and commercial success. What else happened in this era?
Lots. Danny Hillis built the Connection Machine, a supercomputer designed for parallel processing, great for AI and neural nets. Japan launched its big fifth-generation project, aiming for AI-powered computers.
Ambitious government projects, too.
Yep. The Sora architecture for general intelligence was developed. Interval calculus emerged for reasoning about time. You had creative AI like Aaron, the drawing program.
An AI artist.
Kind of.
Yeah. And Ernst Dickmanns in Germany built autonomous vans that could drive on highways. Self-driving cars in the 80s.
Early versions, yeah. Progress in understanding language discourse continued. Minsky published The Society of Mind, thinking about intelligence as cooperating agents. Roddy Brooks pushed for reactive robotics with his subsumption architecture.
Different approaches to building intelligence.
Right. Commercial advisory systems appeared. Chip technology, VLSI, helped build neural nets in hardware. And Dean Pomerlew's LVN drove a van across the country using a neural network.
Okay, that sounds like serious progress, but I feel another winter coming on. The hype cycle strikes again.
You're sensing the pattern. While the 80s were big, expert systems eventually hit limitations. They were brittle, hard to maintain, didn't handle common sense well. And the neural nets, while promising, still needed lots of data and computing power that wasn't quite there yet for massive scale.
So another period of adjustment.
Yeah, the late 90s, early 2000s were a bit quieter again. Not a harsh winter like the first one, maybe, but less explosive growth before the current massive boom kicked off.
Okay, so that brings us closer to today. What finally ignited the firestorm we're seeing now? The third summer, or maybe fourth, depending on how you count.
Two things, really, coming together in a perfect storm. First, data. Just unimaginable amounts of data becoming available from the internet, sensors, everything. Big data.
Right. Fuel for the algorithms.
Exactly. And second, computing power. Specifically, graphics processing units, GPUs.
GPUs from video games.
The very same. Turns out their parallel processing power is perfect for the kind of math needed to train deep neural networks. Suddenly, training huge networks became feasible.
So, massive data plus massive compute power.
Bingo. That combination unlocked the potential of deep learning, those multi-layered neural networks we talked about. Now they could be really deep and learn incredibly complex patterns from all that data.
And the big public moment for this was ImageNet, right, around 2012.
That was the watershed moment.
Yeah.
AlexNet, a deep convolutional neural network, just blew away the competition in the ImageNet image recognition challenge.
It could see better than any previous AI.
By a huge margin. It showed deep learning wasn't just theory, it worked spectacularly well. And that just opened the floodgates for research investment and applications.
And since then, it feels like one breakthrough after another.
It's been incredibly rapid. IBM's Watson winning Jeopardy showed amazing progress in understanding natural language, even puns and tricky phrasing.
Yeah, that was impressive.
Speech recognition got good enough for the voice assistants we all use now. Image and video analysis exploded, facial recognition, self-driving car perception.
Siri, Alexa, Google Assistant.
All powered by these advances, we figured out how to train even deeper networks. And then came the games.
AlphaGo, beating the world Go champion.
A huge milestone. Go is vastly more complex than chess. Many thought that was decades away. AI started beating top humans in Poker 2 games with hidden information.
That seems even harder.
It is. Then AlphaGo Zero learned Go from scratch, just playing itself, becoming better than the original AlphaGo that learned from human games.
Learning without human examples.
And AlphaZero did the same for Go, chess, and Shurgi, mastering them in hours. And then a really fundamental innovation, the transformer architecture.
Transformers. Okay, I hear that term constantly now. Why is it such a big deal?
It came out in 2017. Its key idea is attention, allowing the AI to weigh the importance of different parts of the input data. This turned out to be incredibly effective for processing sequences, especially language.
This is the foundation for things like ChatGPT.
Exactly. It's the engine behind almost all the large language models, the LLMs, that have suddenly become so prominent.
Which brings us smack into the current AI boom, the 2020s. It feels like warp speed now.
It really does. These LLMs, GPT-3, then ChatGPT, models from Anthropic like Claude, Google's models, they showed stunning abilities. Understanding context, generating coherent text, coding, even showing sparks of creativity.
ChatGPT's arrival felt different. Everyone was suddenly using it.
It captured the public imagination like nothing before. And it sent shockwaves through the tech industry. You heard about code red situations at major companies scrambling to catch up or release their own versions.
And it also kicked off a huge debate about, well, everything. The future, jobs, risks.
Absolutely. Intense discussion about the implications, the potential dangers, even calls from some experts to pause development of the most powerful systems.
It's exciting, but also a bit unnerving, maybe. What else is happening in this current wave?
So much. Natural language generation keeps improving. AI, like AlphaFold, basically solved the problem of predicting protein structures, a massive deal for biology and medicine.
Right, that won a Nobel Prize connection.
Yes. We're seeing text-to-video generation now with things like Sora. AI assistants are being baked right into operating systems like Apple
It's
Intelligence.
becoming embedded everywhere.
Investment is pouring in like never before. AI skills are in huge demand, and governments globally are trying to figure out regulation and safety. The Bletchley Declaration, the U.S. Executive Order on AI, trying to get ahead of the curve.
It's just incredible looking back at this whole sweep, from like mythical guardians and clockwork ducks to AI that can write poetry and design drugs. It really shows that cycle, doesn't it? The summers and winters.
It really does. Enthusiasm, breakthroughs, hitting limits, regrouping, then another surge. But what's maybe different now is the sheer scale of resources being poured in compared to those earlier eras.
Yeah, the winters happened partly because funding dried up. That doesn't seem to be the issue now.
Not at all. The investment is orders of magnitude higher, which suggests the pace of change might be even faster and more sustained this time around.
So thinking about this incredible journey, it makes you wonder, doesn't it? As these systems get more and more capable, what does intelligence even mean anymore? How are these machines going to keep challenging our own definition of it?
That is the profound question, isn't it? How do we understand intelligence, creativity, maybe even consciousness, as we continue to build things that seem to exhibit more and more of those qualities?
Yeah. Definitely something to ponder. Well, this has been fascinating. Thanks for taking this deep dive with us today.